Good morning, children. Let us start the new lesson, Current Electricity. In this lecture, I am going to cover the topic electric current, drift velocity, relation between drift velocity and current density. Now, current electricity. As you know that the current, till now we have studied about the charges which are at rest. So charges, they are not really are at rest, they are moving within the material. The electrons in a copper wire are never at rest and they are continuously in random motion. Therefore, it is important to analyze the behavior of charges when it is at motion. The motion of the charges is called the electric current. Now, current electricity is the study of electric charges. Now, we know that the Alexander Volta, who invented the electric battery, which produced the first steady flow of electric current. Modern world depends only heavily on the use of electricity. As you know that right from the early morning till night, if there is no electricity, then life becomes boredom. We cannot do anything without the electricity. So in this unit, we will study about the electric current, resistance and related phenomena in materials. Now, electric current. As we know that matter is made up of atoms. Each atom consists of positively charged nucleus with negatively charged electrons moving around the nucleus. You know that conductors are the substances which have free electrons in abundance. So these free electrons, they are loosely bound to the nucleus and they are free to move inside the nucleus. These free electrons, they move randomly in all the directions. In generally, due to their random motions, there is no net transfer of the charge. There is no net transfer of the charges from one end of the conductor to the other and hence no current. When potential difference is applied, only when potential difference is applied by the battery across the ends of the conductor, the free electrons drifts towards the positive terminal of the battery and produces a net current. Positive charges, we know that they flow from the higher electric potential to the lower potential, and the battery or the electric supply simply creates potential difference across the conductor. So the electric current in a conductor is defined as a rate of charge through a given cross-sectional area A. Now, as you know that water can flow only when there is a difference in the height. When both the ends they are at the same height, then there is no water flow. If one end is at higher and other end is at lower, only then the water can flow. Similarly, when A is at higher potential and B is at lower potential, so current starts flowing from A to B. When A and B both are at the same potential, no current flows. Similarly, charges flow across the area A. Now we will define about the current. If a net current Q passes through any cross-section area in time t, then the current is defined as I is equal to Q upon T. But as we know that charge does not flow always constant, so we define in general average current. I average is equal to del Q upon del T, where del Q is the amount of charge that passes through the conductor at any cross-sections during the time interval del T. So if the rate of at which the charges flow in time, then current also changes. So instantaneous value of the current, if we say that I is equal to limit del T tends to 0, when del T tends to 0, then this expression results to dq upon dt. So current, instantaneous value of the current I is equal to dq upon dt. The unit of the current is ampere. So we can say that 1 ampere is equal to 1 coulomb upon 1 second, or we can define that 1 ampere of a current is equivalent to 1 coulomb of charge passing through perpendicular in section in 1 second. The electric current is a scalar quantity. Now, though current has a direction, but still it is a scalar quantity, and that is why it can be added algebraically. That is, suppose at a point if one current is coming, 4 ampere is current in this direction, the other current is coming also towards this at 3 direction, then in this direction, then the sum of the current will be 7 ampere. They will not be added vectorially. They are simply added algebraically. So it is a scalar quantity, though is at direction that this current is flowing towards the right hand side, this current is flowing towards upwards direction, and this current is flowing in some another direction, but still it is a scalar quantity and not a vector quantity. For an example, you can calculate the amount of the current flowing in this. Here the 120 coulomb charge is flowing through a copper wire in 1 minute. So from this given expressions we can find out that current flowing in the current is 2 ampere. Now direction of the current. Now the direction of the currents, that is the conventional direction. Conventionally the direction of current is taken from positive to negative. It is shown by the green arrow. But actually the current is due to the flow of electrons. So this is the direction of the flow of current, flow of electrons which flow from negative terminal to positive terminal. So the direction of the conventional current and the direction of the electronic current, they are opposite to each other. Conventional current is simply the current and its direction is from positive test charge to move, in which direction the positive test charge move. In typical circuits, the charges that flow are actually electrons from the negative terminal to the battery to the positive. So as a result, the flow of electrons and the direction of the conventional current points is opposite directions. Mathematically, we can say that transfer of the positive charge is same as the transfer of negative charge in the opposite direction. Lightning also produces current, as nowadays you are quite familiar that lightning takes place and current is also produces. So electric current is not only produced in batteries. In nature, the lightning bolt produces enormous lightning current in a short time. During lightning, very high potential difference is created between the clouds and ground, so charges flow between the clouds and the ground. Now ions, you know that all materials, they are made up of they have the free electrons. So the ions, if the outermost electron leave the if the outermost electron leaves the atom, then they have the free electrons and which are responsible for the electric current. And those ions will not move freely within the material like free electrons, hence the positive ions will not give rise to the current. Now drift velocity. So in a conductor, the charge carriers are the free electrons. These electrons move freely through the conductor and collide repeatedly with the positive ions. If there is no electric field, then electrons move in random direction, and so the direction of their velocity are completely in random directions. And when they move randomly in all directions, then the average velocity will be 0. So on an average, the number of electrons traveling in any directions will be equal to the number of electrons traveling in the opposite direction. As a result, there is no net flow of the current in any directions, hence there will not be any current. Suppose a potential difference is set across the conductor by connecting a battery. Then electric field is created in the conductor. And we say that the electric field exerts a force on the electron, producing a current. The electric field accelerates the electrons while ions scatter the electrons and change the direction of the motion. Thus, we have a zigzag path of the electrons. In addition to the zigzag motion, due to collision, the electron moves slowly along the conductor in a direction opposite to that of electric field, and this velocity is called the drift velocity. So we can say that this electron, it is moving in a zigzag way. So the